In this video, we'll continue our discussion on procedures in scope by talking about the special form let. So let's useful when we want to add some local variables into a given scope. And the syntax of a let is as follows. So there's one large combination, starting with the keyword let, and then followed by a sequence of pairs where the first element in each pair is some variable or symbol, and the second element is some expression or value to be associated with that symbol. So in this case, variable 1 gets the value of expression 1, variable 2 gets the value of expression 2, etc., etc. You can have as many of those pairs as you like. And then what follows this definitions area is a body. And the body works just like a procedure body. It's a sequence of expressions, the last of which is the value of the overall let. So let's say a simple example of this. Go over to Dr. Racket here. So let A be 1 and B be 2, and then plus AB. A real simple let here. So the keyword let, then we have our definitions area, and then the body. So this definitions area says bind the symbol A to the value 1 and the symbol B to the value 2. And these could of course be larger combinations. So I could have plus 1, 1 for example instead of the literal 2. And that should do the same thing. So it says evaluate this expression, get the value 2 in this case, and then associate 2 with B. Then when we're running the body of this let, plus A and B here is running within the context of those new variable bindings that we just created. So A has the value 1, B has the value 2, so plus AB should give us 3. And there's a 3. So let creates a brand new scope for its body. And I know I mentioned in a previous video that the only way you can create scopes in Scheme is by executing a procedure. This appears to refute that, but as it turns out, let is actually just a syntactic sugar for a function. We'll discuss that a little bit later on. For now, though, let's take a look at some more examples. So coming back to our square root example here, there's the code for the square root example. A number of functions here, but I'm going to rewrite this good enough function. So here's the old good enough function. I'll leave them both in so we can see them both. Copying and pasting is a bit messy, so let me clean this up a little bit. Something like that seems pretty readable. Right, so the old good enough is not super straightforward to see, right? We've discussed it in the past, so hopefully you can understand what it's doing. But just to look at it, it's square of the guess minus x, absolute valued for some reason, then it's less than this 0.01 value, whatever that value means. One of the advantages of using a let is that it provides symbolic abstraction in places where that doesn't naturally exist. And as we saw before, symbolic abstraction allows us to associate meaningful names with computational values, which can enhance readability and sometimes save temporary results so that we don't have to recompute them a second time. We can just store them to a name and then use that name over and over again. In this case, we're just using it to enhance readability, but take a look at this good enough version that uses a let. So both of these will compute the same thing, so long as our values are the same. So in this case, this new good enough says let tolerance be 0.001. So now we know what that value means. The tolerance tells us a little bit more about what that number represents. Let the difference be the absolute difference between the square of guess and x. So we're squaring our guess, subtracting that from our input value, and then taking the absolute difference between the two. And then what good enough does is says if the difference is less than the tolerance, then it's good enough. If it's not, then it's not good enough. So by using a let, using the symbolic abstraction, associating names to these values, the code becomes a bit more readable. It's a bit more understandable what's actually happening here. And just comment this out so we can prove that it still works. Run this and we'll say square root of 9. What happened there? If good enough guess x. Oh, right, we don't need x here, because we have a free variable for x. Good enough. Oh, sorry, not good enough. Square root. Square root of 9, and we get something close to 3. Okay. So, quick note: the good enough here still has the pass-through variable x instead of the free variable as we changed it to here. Okay. So that's an example. Let's go on to one more example of, I guess, a couple more examples of lets, so we get a sense of how they work and how they don't work. So let's define let example with the argument c, or the parameter c. And the body of this will just be let a be 10, let b be 7, and then plus abc. So try and work out for yourself what will be the value of this expression if I said something like let example 13. So pause the video, try and work it out, see if you can understand how the let will do, and now I'll explain it. Okay, so this example here is fairly straightforward. Our let isn't much different than the let before. So we pass in this 13, so C gets the value 13. Then we say let, so let A be 10 and B be 7, so creating two new variables. And now we have this inner scope of the let, and it says plus A, B, and C. Well, A and B are defined quote-unquote locally within the let, but C here is not defined within the let. It is a variable from outside the let, from the function itself. So within the let, within the body of the let, this variable C is actually a free variable. But it works just like free variables as we've seen, because of lexical scoping as we learned it in the previous video. The nesting of scopes matches the nesting of the text, so let is tucked inside this function, so its scope is inside this function, so it has access to all the variables from inside that function. So A plus B plus C is 10 plus 7 plus 13 should be 30. And there we get 30. All right. Let's do a slightly trickier version. Define let example 2 with the parameter x, and we'll say plus let x be 3. Double brackets here because we have to separate the definitions area as well as the pair, but there's only a single pair. So if we had other variables in here, if I had like y equals 4, for example, we'd have a let that looks like it does before, where we have one set of brackets around the entire definition and one set of brackets per binding. But if we're only creating one variable, then we end up with double brackets for a single binding. It's just how the syntax works. All right, so let x be 3, and then the body of our let will say plus x times x10. Now all of that's still in an addition statement, so let's put an x here as well. Okay, so what is the value of this expression? Let ex2 at 5. So I'll give you a second to work this through, or pause the video and work your way through it, and let's try and explain this. So this one's a bit trickier. The real trick here is that the let has a value, and it's being used in an addition. So in order to do this addition, if we're following applicative order, we have to evaluate all the sub-expressions. So we get the addition operation, which is just procedure for addition. We have the value of this let, which we'll have to walk through manually, and the symbol x. So what is the value of this symbol x here? So if we're outside of the let, the definition for this x comes out of the parameter for our function. In that case, it gets the argument value, which is 5, so we have plus something 5. Now, what is that something? Now, if we walk through this let, it says let x be 3, so we're creating a new local variable called x within the nested scope for the let, and because it's using the same name, it's actually hiding the free variable x from outside. So if we're inside the body of this let, and we say the word x, or the symbol x, we're referring to the local x, not the free variable outside that, because this local one hides the free variable. So if the local variable x is 3, we get 3 times 10 is 30, plus 3 is 33. So the value of this entire let then will be 33. We get 33 plus this x here, which again was from outside, so it's the parameter value, which is the argument here, 5. So we get plus 33 and 5, which should give us 38. Okay. So inside the let, we have an x. Outside the let, we have a different x. And just like if we have nested functions with the same variable names, the inner more scopes will hide the external variables if they share the same name. All right, let's do another one here. If I were to define, what is this code? There it is. Let example 3 with no parameters this time. So if we say let x be 3 and let y be plus x1, there's our definitions, and then real simply x times y. So if I were to run this code, let ex3, notice I don't have to include any arguments because there's no parameters. But if I were to run this, what would the value be? Again, pause, see if you can't figure it out for yourself, and then we'll try it. Okay, so in order to explain this one, I'm first just going to run this and see what happens. So we get an error, x undefined, cannot reference undefined identifier. So I'm just gonna put a space here to get rid of that. So the error here is this x inside the definition of y is undefined, which means it doesn't have a value. No binding exists. But on the very previous line, line 45 here, we said x has the value 3. So shouldn't it be that on line 46, x has the value 3? Well, as it turns out, a let doesn't work like that. The bindings that a let creates exist only within the body of that let. They don't yet exist while we're walking through the remaining defines. So x equals 3 doesn't happen, or doesn't properly happen, until we're inside the body. Then when we reference x, it has a value. If we're outside of this body, though, we're still technically just in the function scope, the let ex3 scope here. So this x doesn't have a value because there's no local or global x outside of this let. Okay? Inside the body, this is perfectly fine. So the error here is this x here doesn't work. And I can prove that by just changing this to a 1 for now, just see how this works. Run this code real quick. There you go. So this x is fine, as we've seen before. Once we've defined a variable within our let statements, they have values and we can use them. But we can't use them inside the binding section, inside the place where we're creating the variables. Okay? There's 2 ways to fix this. The first way is to just use nested lets. So we could say let x be 3, and then inside the body of that let, so we'll just say that's the entire definitions area. Then inside the body of that, we'll say let, and then we'll make a new binding for y. Now, because this let is inside of this let, when we say x, we're inside the body of this let. So x3 does in fact exist. Okay, so here we say let y get the value of x plus 1. And then in the body of that let, we have x times y. Okay. And if we run this, we should get, if x is 3, y will be 4. 3 times 4 should be 12. And we get 12. Wonderful. So that's one way to solve it, just use nested lets. It can be a bit of a hassle, though, to have to nest a let every single time. So just create a new version here. Define let ex3b, just so we have a separate version here. So the old version of let looked like this. Let x be 3, let y be plus x1, and that's all of that, and then times xy. And this was the error version. If we try running this code, it will crash again with the same error. Just make sure of that first before I try and fix a bug that's not there. Okay, so same error, x is undefined. So one quick way to fix this is instead of using a let, we can use what's known as a let star. So let with an asterisk technically is a different special form, and it actually maps to this nested version of a let. So it says for each one of these binding expressions, or binding pairs, create a brand new let and nest it within the external let. So create a let for x3, and then inside that put a let for y is x plus 1, and then because that's it, then we just run the body there. So saying let star translates in the background to this nested form of let, but we can run it and get 12 without having to do all the nesting ourselves. So nice little shortcut there. There's other versions of lets out there as well. I'll leave you guys to explore them as you will. But that's pretty much it. So you might be asking, why would I use let? Why wouldn't I just use defines everywhere? So a let can be used pretty much anywhere a function call is used, whereas internal defines have to be put at the top of a function body. Okay. Here, I'll show you an example where these two distinguish each other, or distinguish from each other. So define using def first. If x is greater than 0, then we'll do 2 things. We'll create a variable, and then we'll add that variable to x. We'll say begin. Remember, begin creates a sequence of expressions. Because we want to do 2 things inside this if statement, we need a begin. Otherwise, it'll take one as the then part and one as the else part. If we say a begin, they're all being tucked into the then part. So begin, define y to be 7. Oops, 7. If I could type would be nice. And then just plus xy. So that closes the begin, closes the if, and closes the whole thing. So if x is greater than 0, we'll do 2 things. We'll define y to be 7, and then we'll add 7 to whatever x was. It's a bit of a meaningless example, but it'll highlight an important point, or an important difference between lets and defines. So let's call using def with, I don't know, 17. So if I run this code, it crashes. Define is not allowed in an expression context. And And this is what I was saying. Defines need to be at the top of your code. Now, if we know that y is always going to be 7, or if we knew at the outset that it was going to be 7, that wouldn't be a problem. We could just put it right at the top, and we could just use y wherever we need to. But it's entirely possible that in one case, when x is greater than 0, we want y to be 7. But if it's less than 0, or in all other cases, we want it to be something else. In that case, you need that variable binding to happen closer to the actual usage, not just at the top of your function. And this is where let is particularly useful. We can use lets anywhere a regular expression, not a regular expression, but anywhere a normal expression would be put into our code. So let's see this same example using lets. Define using let x. If x is greater than 0, say, we don't need to begin because let kind of does that for us, gives us the whole sequencing. I could say let y be 7. And that's the only binding we need, and then the body of that let plus xy. And now this highlighted bit here, this let expression has a value, so it can be used anywhere that any other expression is needed, anywhere that a value is required. In this case, a value is required as the quote-unquote return statement of this function, so the let will suit that need. And if we run this code, oops, helps if we comment out our old error, and probably run this new code using let, same value, run it. Oh, still tries to define that. Okay, well, let's get rid of this bad example then. Try one more time. There we go. So 24 is the answer here. 24 plus 7 gives us, or 17 plus 7 gives us 24. So it runs fine with no errors. So the key difference there is that defines have to be used at the top of a function body, whereas lets can be used anywhere an expression is expected. Also, if you get in the habit of using defines, it encourages sort of imperative style programming, where the focus is on variables or changes in memory, instead of on functional transformations or the substitution model, as in functional programming. So I recommend always use lets when appropriate. Stick to using defines only for creating functions and for defining top level or global constants. For everything else, if you need local scopes, you need to add some extra variables to a local scope, use lets. They're a bit more explicit in terms of what they do, and there's a lot fewer hidden surprises in store. All right, that's it for this video. In the next video, we'll take an introductory look at activation records in the call stack and how they apply to Scheme.